Hello folks, fellow YouTubers and friends, and welcome again to Boomtown Laboratories, where we are dedicated to the research and development of the two-stage oscillator. Some people are starting to call it TSO. I think it's nice. It's short, sweet, to the point. Last video, I said it would be 3 parts. This is part 2. We were working with the rack and pinion to run the two-stage oscillator, rather the pendulum, and at times we would get it balanced out, but it wouldn't go high enough to produce any genuine power. It would produce power, but not what I want. And every time we tried to rework it to make it go higher, then it would take days, it seemed like, to balance the thing out again. So anyway, one of my earlier videos, I had it was called Escapement That Really Works for the two-stage oscillator. Anyway, it was nothing more. It was very crude, just a table saw blade, 10-inch blade. No, it was a skill saw blade, 7¼ inch blade that I took my plasma torch and had cut out and tried very crudely and deliberately crude to make a W17 escapement, which is Ben Van de Waal on YouTube has many escapements built out of Legos, and that was the one that I picked and tried to reproduce to push the pendulum. Now, in his, he swings the pendulum a little bit like a grandfather clock. I, on the other hand, am trying to swing a heavy pendulum a lot higher. So, deliberately building it with a lot of friction and very crude, and it worked. So then I came up with the idea of this, right here. This is not a saw blade. This is cut out of 2 pieces of 1/8 inch steel. I think I showed this to people earlier. This is a spool of that was for welding wire, for a wire welding machine. The inside diameter where the string is wrapped around is 2 5/8 of an inch. Now the wheel has 8 points, so if you take the circumference and divide it by 8, each time the catch is lifted and it comes around and catches again, that's how far you get a pull of 10 pounds, because there is a 20-pound bottle hanging on a 2-part line. So consequently, the string has a 10-pound force pulling right here for 1/8 of its circumference on the inside. All right, now that's how much force it takes to drive the pendulum. The pendulum total weight, arms, steel pendulum, and the lead inside, and the block of lead we have on top, total weight is 375 pounds. This will push it almost 90 degrees. Flaw in building the two-stage oscillator, I can't get it to go 90 degrees because of the pivot point on the power transfer bar. Next machine that will be built in such a manner that the pendulum can go a full 90 degrees. Okay, I'm going to fire this bad boy up in a minute and let you see how it does work. However, being human, I did make a mistake in this build. 2 of these wheels, well, in fact, the whole thing is off center, which means that this one is closer to center than this one. This one is further away than this one, but closer than this one. So consequently, the one that's the longest, when the pendulum comes up and tries to release the catch, it does fine until it hits that long one. When it hits the long one, it doesn't push it up high enough to release. So at that point, I have to give it just a little nudge. So you're talking about 7 or 8, maybe 9 swings before it doesn't do it. But it does power it for that length of time. Now all I have to do is just a little touch. We're building a new one, and we've already got it so accurate, there's not a 1/64 of an inch difference from center to the tips of all the wheels, and the wheels on the new one will not be washers on bolts. They will be actual bearings. We bought and ordered special bearings. They should be in Monday. Today's Saturday, okay? September the 10th, 2011. Okay, so anyway, when we get that, we'll put that on the machine, adjust it out, which takes very little time to do. Now right now we have the work bar over here. The bar that actually does the work is a 7-to-1 ratio from the pivot point of the pendulum to the lift part of the work bar. It takes 124 pounds to keep it from coming up, and even then the pendulum is trying to raise it. Okay, so in locking it down, and this will be the last demonstration I do with it locked down, because the actual pivot point of the pendulum itself is flexing that 8-inch heavy-duty channel iron 3/8 of an inch. Now with the ratio I've got, and only allowing the work bar to come up 5.5 inches, then the pendulum pivot point will only move roughly 3/4 of an inch up and down, but it's already flexing 3/8. And the W17 escapement by Ben Van de Waal does power it. Okay? Now, once we get it all powered up and locked in where it's powering it, then we're going to remove 62 pounds of the 124 pounds. This will allow the work bar to come up with a 62-pound force. With the double Beckett, it'll be pulling on the chain. Therefore, it won't slam up and start tearing things apart, because it's going to actually be making electricity. So there will be a resistance. However, when the pendulum comes up all the way up to almost 90 degrees, when it stops, it does not have any weight. Therefore, the 62 pounds weight of the work bar will pull down on the chain with the double Beckett on the other side, keeping the chain going in the same direction. Okay? So, with all my excuses made and this, that, and another, let's fire this bad boy up and see what she's going to do. All right? Alright, it's going to stop here in a second, but it is powering it. You can see that. Stop right here. Nope. There you go. Okay. All right, we're definitely on the right track. She's definitely trying to pick her up right over there. We're talking 11 inch-pounds of force to drive the pendulum, but it's not going up and down, except for that flex in the metal. We're going to find out. We're going to get the other one built so it's more accurate, runs better for longer, and then we're going to release the work bar and see what happens. See you next time.